Welcome to qnawire.
So now we'll work on problem 58 from chapter 17. In this problem, we're asked to calculate the solubility of lanthanum fluoride, LaF3, in grams per liter in three situations. And the first is in pure water. So let's go ahead and write the values that we're going to need for this. So for LaF3, the KSP is equal to, we can find from Appendix D, 2 times 10 to the negative 19. And the molecular weight we'll need, because we're asked to calculate in grams per liter, is 195.9 grams per mole. So we're asked to calculate the solubility first in pure water. So we can set our KSP equal to the expression for KSP. So KSP is equal to 2.2 times 10 to the minus 19, which is equal to the concentration of lanthanum, 3 plus, times concentration of fluorine, cubed. And so we can substitute x and 3x here, and we get a value. If we go ahead and work this through, we get 3x cubed, which is 27x cubed, times x is 27x to the fourth power. So we have to divide both sides by 27 and take the fourth root, and then we get x is equal to 9.28 times 10 to the minus 6 molarity. And if we multiply by the molar mass, we can get the solubility in grams per liter, which is 1.82 times 10 to the negative 3 grams per liter. So in part B of this problem, we're asked to calculate the solubility in a 0.01 molar potassium fluoride solution. So here we have a common ion in fluorine. So we can go ahead and write the expression here for the dissociation of this element, this compound. So you have LaF3 dissolving to form the lanthanum ion and 3 fluorine ions. So if we write our ice chart, we have no initial lanthanum, but this time we do have 0.01 initial fluorine. So we add x and we add 3x. We get a equilibrium value of x for lanthanum and 0.01 plus 3x for fluorine. So we can now calculate our x value. So our KSP is 2 times 10 to the negative 19, which is equal to x times 0.01 plus 3x. But since our KSP is very small, we can eliminate this addition of x, and we get simply x when we cube 0.01 times 1 times 10 to the minus 6. So we solve for x, and we get x is equal to 2 times 10 to the minus 13 molar. And when we multiply by the molar mass, we can see that the value is 3.92 times 10 to the negative 11 grams per liter. So we can see that this has dramatically decreased from the value of 1.82 times 10 to the minus 3, which we got in pure water. So the common ion in this case dramatically reduces the solubility. So in part C, we're given a third situation, which is in 0.05 molar lanthanum chloride solution. So this time lanthanum is the common ion. So we can go ahead and write our dissociation of this ionic compound. into lanthanum and fluorine. So this time we have an initial concentration of 0.05 for lanthanum, nothing for fluorine. We add X and 3X again, and we get 0.05 plus X and 3X. So our KSP is 2 times 10 to the minus 19, which is equal to 0.05 plus X times 3X cubed. So we eliminate this addition of the X, which gives us a value equal to 0.05 times 27x cubed, which is equal to 1.35x cubed. So we solve for x by dividing both sides by 1.35 and taking the cube root, and x is equal to 5.29 times 10 to the minus 7 molar. And if we multiply by the molar mass, 195.9, we get a value of 1.04 times 10 to the negative 4 grams per liter. And since the initial concentration of lanthanum is not as high as the initial concentration of the fluorine from the previous page, the solubility is not as drastically reduced, but it is reduced compared to pure water.